Hello, today we're going to talk about the history of the discovery of atomic structure. I will warn you that my dog is here with me and he's very jealous of the fact I'm talking to you and not to him, so he may come in here and bother us. If I can do this without messing up the camera. Can you say hi, Ted? I can't do that very well, sorry. That didn't work, did it? This is Teddy. Teddy's driving me crazy right now, so I'm just going to show you who he is. So if I talk to him during the video, you'll know what we're doing. Alright. This video is on the history of the discovery of the atom. Or not really discovery, but kind of how we learned all about the atom. Alright? Science is full of history. We have so many different historical things that we could talk about this all day long. And here's Teddy bringing me his tennis ball. Here you go. But we're going to talk about the atom and how we came to know the atom as we know it today. We'll start with the Greeks, Democritus and Aristotle. Democritus, this guy right here, it's a painting. It's not a picture of him. I know you're excited. They were philosophers. And something you need to understand, philosophers were people who sat around and thought. But alchemists were also referred to as philosophers. Now, alchemists were the earliest chemists. And they're around in the Middle Ages and were trying to create gold out of any other metal. And they were also called philosophers. In fact, J.K. Rowling named the first Harry Potter book, Harry Potter and the Philosopher's Stone. And if you buy a copy that is published in Britain, that is the title of the book. But they figured the Americans were too stupid to know what that meant, so they switched it to Sorcerer's Stone for us. It's actually very interesting. The first couple Harry Potter books, they use a lot of terms like jumper for sweater, and they change it for the Americanized version. Now, later on, they don't bother to change it because they assume we've all figured it all out by then. But I digress. These guys were philosophers, which meant they sat around and thought about things. And Democritus sat around and thought, decided, if you were to cut something in half, and cut it in half again, and again, and again, and again, eventually you would come to a piece that could not be cut any further. He called that a tomos, which meant indivisible. Aristotle came up with the idea that all matter was made of either earth, wind, fire, or water. And so they kind of started the whole thing. And of course, Aristotle, a lot of his teachings, including that the thought that the earth was the center of the universe and not the sun, the center of our solar system, so on and so forth. All of that, they influenced us heavily. All right. So, if we go past the early alchemists and we get to the early chemists, John Dalton was an English chemist, and he came up with the first modern atomic theory. And what I mean by that is that he came up with definitions that agree with our definitions of elements and compounds. He said that an atom was a solid sphere, like a billiard ball, or a pool ball, if you will, and he came up with the idea of the law of constant composition, which defines a compound. The best way to illustrate that is with a little joke. Okay, now of course we can't see it very well. Let's zoom in, shall we? So here's our little joke. He says, I'm a chemist, so I'll just have some H2O. The waiter's taking the drink order. The other guy says, LOL, I'll have some H2O too. So he brings them their drinks, and the chemist drinks his, and the other guy drinks his, and dies. Because the chemist ordered H2O, but this guy said, I want H2O2. That is hydrogen peroxide. Completely different things. Peroxide, which is what you put on your hair to bleach your hair. Okay, back in the day, they used to do like the ends one color and the crown a different color, and that's what they would do is they would put the bleach right on there. The peroxide right on there. Peroxide is what will bleach hair. All right, so that's the law of constant composition. Water is always H2O. If it's not H2O, it's not water. Peroxide's H2O too. Even though they're both made of hydrogen and oxygen, and water has a mass of 18 grams per mole, peroxide would have a mass of 34 grams per mole. So they have different masses, which is obvious, but they also have different ratios of hydrogen and oxygen. And that is what the law of constant composition is. All right, now I need to zoom back out. If I was Miss Rice, I would edit all that out, but I'm not going to worry about it. Dalton's theory. All elements are composed of atoms. Works. All atoms of a given element are identical. So all gold atoms are gold. All silver atoms are silver. Silver is different from gold. Atoms of different elements are different. Compounds are consisted of two different elements. Now, you guys have heard of O2, that's oxygen. Oxygen is diatomic. It occurs in pairs. CO2, carbon dioxide, has a carbon bonded to two oxygens. Okay? O2 is not a compound. It's still an element. It's just always in pairs. CO2 is a compound because it's made of a carbon and two oxygens. Also, he came up with the idea atoms are not created or destroyed in a chemical reaction. What you start with is what you end with. Those of you that have ever balanced equations before know what we're talking about. Okay? Here is a picture. This is from the Compound Interest Chemistry website, and he does all these infographics. I got to meet him this summer. He was really cool. He talked at our conference. But these are some of the different, and again, I'm going to zoom back in. I zoomed out. Some of the different symbols he used for the different elements. Okay, oxygen was just a circle, hydrogen was a circle with a dot in the middle, so on and so forth. He came up with these different symbols. I just thought that was kind of cool. I thought you'd like to see that. All right. Let me get back up here. So, Dalton, my mouse has too much strength. Dalton's ideas hold, but then we get to about the turn of the century, and J.J. Thomson is messing around with gases, and he has a big tube of gas. That tube has, probably, well, I don't know what it was. I can't remember. I'll have to look that up and come back to you. But it has a tube of gas in it, and he is running an electrical current through it. It's kind of like, you guys know fluorescent light bulbs. If you look up at the ceiling in the classroom, you see fluorescent light bulbs. That's just gas, and that has an electrical current running through it. Neon lights are gases with electrical currents running through it. So here he has a gas-filled tube. He's got metal plates on both ends, and he's got electricity flowing through it. Okay? As that electricity flowed through, he had a, I guess I better draw it. I guess I'm going to draw it. He brought a positively, okay, so here's our electricity going through it. You could see a stream of something, plasma, if you will. Okay, he brought a positively charged plate near it. Okay, you know that magnets have a positive and negative charge. He brought a positively charged plate towards it, and the electrical stream bent towards it. Then he got a negatively charged plate, and when he brought that up next to it, it bent away. That didn't bend very much. I'm having a little trouble there. Hopefully you get the idea. It pushed away. Like particles attract, opposites attract, like particles repel. So he determined that this stream was negative. Now he knew an atom was neutral, So if they've got negative particles in it, there must be positive particles in it. And that is what he came up with. And we call this the plum pudding model. It actually works better to think about it as a chocolate chip cookie, because we, again, are not British, so we don't really understand what a plum pudding is. A plum pudding is like a very moist fruit cake, if you will. But the electrons were like the fruit in a fruit cake, or the chocolate chips in a chocolate chip cookie. And then the rest was positively charged that balanced out that the negative part. So, same time, Ernest Rutherford is studying. He's working with Becquerel and working on radioactivity. Okay, they've discovered radioactivity, and they've discovered what they call alpha particles, which are particles given off when some substance decays, when it changes from one element to another. And when it does that, it emits particles. It can emit an alpha particle, a beta particle, or a gamma ray. Gamma rays, you know, that's what gives the Hulk his superpowers. Well, an alpha particle is basically a helium atom, and it doesn't have any electrons. So it's just 2 protons and 2 neutrons. So he's messing around with alpha particles, and he sets the alpha particles up and in a box. And he takes a piece of gold foil, and I know it doesn't look like foil, it's supposed to be 3 gold atoms. He takes a piece of gold foil, and he puts the box, this may give you a little bit better idea of it. Here's the alpha particles. They've got a box with a very small slit in it. It's allowing those particles to come out. They're moving at the speed of light. Here's the gold foil. Now, if the plum pudding model held, all of those particles would have gone all the way through. End of story. But instead, some of them bounced back and hit this screen that was set up to detect that light, because alpha particles are moving at the speed of light. And so it would detect those alpha particles hitting it. And they described it as being a surprise, as if they would have launched a shell or a cannonball at a piece of Kleenex, and it bounced back off the Kleenex. That's how surprised they were. What that meant is there had to be something in there that was a solid. Okay, and if we look at this picture, here we have 3 atoms. If they had all gone straight through, that would have told people that there wasn't anything solid. It was just that matrix. But instead, some of them hit that nucleus and bounced back. So Rutherford came up with the idea of a nucleus, a small, densely packed nucleus, and then a whole lot of stuff roaming around the outer edges. Okay, here is Rutherford's model. If Rutherford's model had held true, everything would have gone straight through, but instead what happened is the alpha particles came through. When they hit the nucleus, they bounced off. So Rutherford came up with the idea of a positively charged nucleus. Okay. Now, Niels Bohr studied light and hydrogen gas, and he determined that really, no, the electrons were orbiting instead of just kind of every which way, like in this picture. I don't know what I just did there. Why me? I've already done him. Why won't this go back? Come on, go back. There we go. Instead, what he came up with was what they call the solar system model. Can't talk. Solar system model, saying that the electrons orbit in a specific orbit as they go around the nucleus. Okay, that was Niels Bohr. Following Niels Bohr, we have Schrödinger. Erwin Schrödinger came up with the idea that really, no, he used math, and that the particles were not just in a specific energy level. We didn't know really where they were. We could tell either where they were or how fast they were moving, but not both. It's called the uncertainty principle. And so they determined that really they were in a cloud. Okay? The nucleus was in the center and the electrons were somewhere out there in a cloud. So here is, and this is in your notes, here's the solid sphere model, the plum pudding model, Rutherford with his nuclear model, the planetary model, if you will, Niels Bohr, and Schrödinger with this idea that we had electron clouds. Okay? He used calculus and all sorts of math to take Bohr's calculations for the energy of the electrons as they moved around within the atom, and he came up with these different models, which is the quantum model, and we will talk about that later. All right, thank you.